Today is February 5th, 2026. If you are new to the channel, welcome to Mind Hierarchy. If you have seen the news, then you may have caught this. A Philadelphia woman finds her Honda Civic completely encased in ice. That is just the beginning. Now the clock is ticking on a significant climate event. Beginning around February 10th, a massive influx of Arctic air is predicted to push into regions unaccustomed to such extremes, potentially impacting vast areas across two continents. This deep freeze has developed with little public awareness. Well, at least not the full picture, to say the least. The coming cold won't be typical winter weather. It's a severe, penetrating cold that poses a real risk. Within moments, it can cause physical discomfort and numbness, challenging the body's limits. The primary concern is its predicted duration. Not a single day, but a prolonged stretch that will test infrastructure and personal preparedness on a widespread scale. With Winter Storm Giana off the Carolina coast, a bomb cyclone formed in place where they almost never happen. 6 to 12 inches of snow, 40 mph winds, state emergencies already declared across Virginia, North Carolina, and South Carolina. But here's what they're not telling you. This isn't just bad weather. This is a pattern that started, as some experts say, 20 days ago. But in reality, it starts way beyond and deeper than what us normal citizen will truly know. When the strongest solar storm in 23 years hit Earth. The Polar Vortex collapsed immediately afterward. Meteorologists said it would reset. It has not. Between the storms, there was a global earthquake swarm. Something connected these events, and nobody is saying what. Stay with me until the end, because what is happening to our planet in February 2026 is not being explained, and the pattern is only getting worse. If these anomalies have you unsettled the way they have me, make sure to hit like and subscribe so you don't miss a single update as this continues to unfold in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you've been affected by the extreme weather hitting multiple continents right now. Let's talk about what just happened and what's about to happen next. Winter Storm Giana left a mess across North and South Carolina, dumping up to a foot of snow in some places, wreaking havoc in an area not used to big winter storms. And if you live in the Carolinas, you need to pay attention. This is not your typical winter weather event. This is a bomb cyclone developing in a place where bomb cyclones have no business existing. The meteorological term is rapid cyclogenesis, which means atmospheric pressure is dropping so fast that the storm is essentially exploding into existence. We're talking about a pressure drop of at least 24 millibars in 24 hours. That generates winds in excess of 30 to 40 mph, heavy snowfall, and coastal flooding, all happening at once in regions that rarely see snow accumulations beyond a dusting. Right now, emergency managers across North Carolina, South Carolina, and Virginia are watching forecast models that show 6 to 12 inches of snow, maybe more in elevated areas, combined with sustained winds that will create whiteout conditions. State emergencies have already been declared. People are being told to stay off the roads. And here's what nobody is saying out loud, but everyone is thinking, this should not be happening. Not here, not now. Not like this. But here's the thing that makes Giana more than just an unusual storm. Giana is not an isolated event. Giana is forming while the polar vortex, the massive circulation of cold air that normally stays locked over the Arctic, remains in a state of disruption that was supposed to have ended weeks ago. 20 days ago, the strongest solar storm in 2 decades hit Earth's magnetosphere. The polar vortex collapsed almost immediately afterward. Meteorologists said it would recover in 7 to 14 days. That is the normal pattern. That is what the models predicted. That is what has always happened before. It has been nearly 30 days. The vortex has not recovered. It begs the question, what is causing this? The jet stream, that river of high-altitude wind that normally flows in relatively smooth waves from west to east, is still kinked and contorted into shapes that forecasters describe with words like unprecedented and anomalous. Cold air that should be contained over the Arctic continues to spill southward in massive lobes, setting up conditions for storm after storm to intensify as they encounter moisture from the Gulf of Mexico and the Atlantic. So let me be clear about what we are looking at here. We have a solar storm that hit Earth on January 10th. We have a polar vortex that collapsed in response and has not reset. We have a major winter storm earlier this month that killed people and left over 1 million customers without power. And now we have Giana, forming in a pattern that feels less like random weather variability and more like a planetary system stuck in a feedback loop it cannot escape. The question nobody wants to ask, but everyone should be asking, is this: when a massive atmospheric system fails to recover on schedule, when the normal corrective mechanisms do not activate, when the zipper that is supposed to snap back into place just stays broken, what does that mean? What are we not being told? And more importantly, what happens next? To understand why this matters, you need to understand what the polar vortex actually is. Imagine the Arctic as the center of a giant spinning top. The polar vortex is the rotation itself, a persistent large-scale cyclone of extremely cold air that sits above the North Pole during winter months. This vortex extends from the surface all the way up into the stratosphere, the layer of atmosphere above where most weather happens. The stratospheric polar vortex is especially important because it acts like a containment field. When it is strong and stable, it keeps Arctic air locked in place. The jet stream flows in relatively smooth waves around the mid-latitudes, and weather patterns remain predictable. But when the polar vortex weakens or becomes disrupted, everything changes. The jet stream becomes wavier, more meridional in meteorological terms, meaning it develops exaggerated north to south undulations instead of flowing smoothly west to east. These deep troughs in the jet stream allow Arctic air to plunge far southward, while simultaneously pulling warmer air northward in between the troughs. The result is wild temperature swings, persistent cold outbreaks in some regions, and ideal conditions for powerful storms to develop along the boundaries where cold and warm air masses collide. Think of the polar vortex like a giant atmospheric zipper that normally holds the cold air in place. When the zipper breaks, the Arctic spills out. But here is the critical point. The zipper is supposed to repair itself. The vortex is supposed to reorganize, usually within 1 to 2 weeks. The atmosphere has built-in corrective mechanisms, feedback loops that restore equilibrium. Except that is not what is happening in February 2026. The vortex disruption began right after January 10th. And here we are, approaching the end of the month with no recovery in sight. Forecasters keep showing models that suggest the vortex might re-strengthen next week, but next week keeps arriving and the pattern persists. The jet stream remains stuck in an amplified configuration. Cold air continues to flood southward in waves, and storms keep forming, one after another, feeding on the temperature contrast that this broken pattern creates. Now, some of you might be thinking, okay, so the polar vortex is disrupted longer than usual. Weather is chaotic. Climate systems are complex. Maybe this is just natural variability on the extreme end of the distribution. And sure, that is possible. But when you are dealing with a system as fundamental to hemispheric weather patterns as the polar vortex, and when that system refuses to behave according to every historical analog we have, you need to start asking whether something deeper has changed. You need to start looking at what might have triggered this disruption and why the normal recovery process is not happening. That brings us to January 10th, 2026. That brings us to the solar storm that nobody is talking about in connection with what is happening in our atmosphere right now. That brings us to the question of whether space weather and Earth weather are more connected than mainstream science is willing to admit. Let me take you back to January 10th, 2026. Most people were not paying attention to space weather that day. Most people were going about their lives, completely unaware that the sun had just hurled a massive cloud of magnetized plasma toward Earth at speeds approaching 2 million miles per hour. But space weather forecasters were paying attention. Solar physicists were paying attention. And anyone monitoring real-time data from satellites orbiting our planet knew that something significant was about to happen. The sun had erupted. An X-class solar flare, the most powerful category on the classification scale, had erupted from a particularly active region on the solar surface. Actually, let me clarify the timeline here, because there is some confusion in the public record. On January 10th, a coronal mass ejection began its journey toward Earth following solar activity earlier that week. Then on January 18th, another powerful X-class flare erupted. The coronal mass ejection from the second event arrived at Earth on January 19th and 20th, producing severe geomagnetic and radiation storms. So we actually had multiple solar events in rapid succession. But the key inflection point appears to have been that initial coronal mass ejection that began its Earth-directed trajectory around January 10th. Now, before I go further, let me explain what we are actually talking about when we say coronal mass ejection. The Sun is not a solid object. The Sun is a roiling ball of superheated plasma held together by its own gravity and threaded through with powerful magnetic fields. Sometimes these magnetic field lines become so twisted and stressed that they snap and reconnect in violent eruptions. When this happens, enormous quantities of plasma, billions of tons of electrically charged particles, get hurled into space. If one of these eruptions happens to be aimed at Earth, the plasma travels across 93 million miles of space until it slams into Earth's magnetic field. Think of it like this. Earth sits inside a protective bubble called the magnetosphere, generated by the churning of molten iron in our planet's core. This magnetic field deflects most of the charged particles streaming constantly from the Sun in what we call the solar wind. But when a coronal mass ejection hits, it is not the gentle solar wind anymore. It is a tsunami of plasma crashing into that protective bubble, compressing it, distorting it, injecting enormous amounts of energy into Earth's magnetic field system. The result is a geomagnetic storm. On the night of January 19th into the 20th, Earth experienced a severe geomagnetic storm rated G4 on the NOAA scale, which goes from G1 minor to G5 extreme. At the same time, radiation levels spiked to S4, also classified as severe. These storms generated auroras visible as far south as the southern United States. They disrupted satellite operations, they stressed power grids, and according to data from Earth.com analysis of NASA observations, they created something unusual: transient radiation belts. The Van Allen radiation belts are two donut-shaped zones of charged particles trapped by Earth's magnetic field. They sit above the atmosphere, held in place by magnetic field lines like beads on invisible strings. Normally, these belts are relatively stable, but powerful geomagnetic storms can temporarily create new, ephemeral radiation belts by injecting high-energy particles into regions of the magnetosphere where they get temporarily trapped before dispersing. This phenomenon is still not completely understood. Scientists are still mapping out the complex interactions between solar wind plasma, Earth's magnetic field, and the atmospheric chemistry in the ionosphere, that electrically charged layer of atmosphere between about 40 and 600 miles above the surface. Here is where things get interesting. The ionosphere is not separate from the atmosphere below. The ionosphere is part of the atmosphere, just the upper part where solar radiation is so intense that it strips electrons off atoms, creating a soup of ions and free electrons. This ionospheric layer plays a role in radio wave propagation. It interacts with the magnetosphere above and the stratosphere below. And when the ionosphere gets hammered by a powerful solar storm, the chemistry changes, the temperature changes, the electrical conductivity changes. Now, mainstream meteorology will tell you that space weather and tropospheric weather, the weather we experience at the surface, are almost entirely decoupled. The ionosphere is too high up, they will say. The energy transfers are too small. There is no plausible mechanism for a solar storm to directly influence jet stream behavior or polar vortex dynamics. And to be fair, that is the consensus position based on current understanding and modeling capabilities. But here's the thing about scientific consensus. It represents the boundaries of what we can currently prove with existing tools and frameworks. It does not represent the limits of what is actually true, because there are mechanisms, speculative and poorly understood mechanisms, by which space weather might influence atmospheric behavior. Changes in ionospheric conductivity can alter the global electric circuit, the vertical flow of current between the ionosphere and Earth's surface during thunderstorms. Changes in upper atmospheric chemistry can influence ozone concentrations in the stratosphere. And ozone is a radiatively active gas that absorbs ultraviolet light and generates heat. Changes in magnetosphere magnetospheric dynamics can influence the precipitation of high-energy particles into the polar regions. And these particles can affect stratospheric chemistry through complex reaction chains. Are these effects large enough to disrupt something as massive as the polar vortex? Current models say no, but models are approximations of reality, not reality itself. What we do know is this: a powerful solar storm hit Earth on January 19th and 20th. The polar vortex, which had been showing signs of weakening in early January, went into full disruption shortly thereafter. And instead of recovering on the expected timescale, it has remained disrupted for nearly 30 days. That is not proof of causation, but it is one hell of a correlation, and correlations that strong demand investigation. The timeline mystery is this: why would an atmospheric response linger for so long? Even if we accept that the solar storm somehow nudged the vortex into a more disrupted state, atmospheric dynamics are supposed to be inherently self-correcting. Energy imbalances drive circulation changes that restore equilibrium. Waves in the atmosphere propagate, disperse, and dissipate. The system should relax back to its baseline configuration, unless it does not. Unless some threshold was crossed where feedback loops began reinforcing the disrupted state rather than correcting it. Unless the solar storm did not just perturb the vortex, but fundamentally altered the boundary conditions in which the vortex operates. That is the speculative territory we are entering here. And I want to be clear that we are speculating. But we are speculating because the official explanation, which is essentially that this is all just normal variability and nothing unusual is happening, does not align with the observable facts. The polar vortex has been disrupted for nearly a month. That is not normal. That is not typical variability. That is a system failure, and we need to start treating it as such. In early January, the meteorological community was buzzing. Social media feeds from weather forecasters and climate scientists were full of graphics showing the polar vortex being displaced from its normal position over the North Pole. The jet stream was developing wild amplifications. Cold air was poised to plunge southward across North America. Headlines appeared in weather blogs and specialist news sites. Polar vortex disruption to bring Arctic outbreak. Major pattern shift as stratospheric warming event unfolds. Severe weather Europe. A reputable forecasting site ran detailed technical analyses of the vortex displacement and what it would mean for surface weather patterns in the following weeks. Nobody was denying that the polar vortex had been disrupted. This was stated matter-of-factly, with the kind of calm technical precision that meteorologists use when describing atmospheric phenomena. The disruption was real, measurable, and significant enough to drive major weather pattern changes. Forecasters expected a multi-week period of cold and stormy weather as a result. This was not fringe speculation, this was consensus. But then something interesting happened. As January progressed and the vortex failed to recover, the language started to shift. The disruption was reframed as typical winter variability. The persistent pattern was described as not particularly unusual for this time of year. The connection between the solar storm and the vortex behavior was quietly dropped from most public-facing communications. Not because anyone proved the connection wrong, but because the uncertainty was too high, the mechanism too speculative, the risk of appearing to promote fringe ideas too great. This is how science communication works in practice. Scientists and forecasters operate under intense pressure to be accurate, to avoid false alarms, to maintain credibility by staying within the bounds of what can be definitively supported by data and models. When faced with an anomalous pattern that does not fit neatly into existing frameworks, the safest move is to downplay the anomaly, to contextualize it as a rare but not unprecedented fluctuation, to avoid making causal claims that cannot be rigorously defended. The problem is that this cognitive bias toward conservative interpretation can cause us to miss genuinely novel signals. When a system behaves in a way that falls outside historical norms, describing it as typical variability is not just misleading. It is potentially dangerous. It creates a false sense that we understand what is happening when we do not. It discourages the kind of urgent investigation that anomalous behavior should trigger. Let me give you a concrete example. The The jet stream is normally described as a relatively smooth westerly flow in the upper atmosphere, meandering in gentle waves as it circles the globe. But when the polar vortex weakens, the jet stream becomes wavier, more meridional, developing deep troughs and ridges that create large north-south excursions. This wavier jet stream is what allows Arctic air to plunge far south while simultaneously pulling subtropical air far north. It is the engine that drives temperature extremes and creates ideal conditions for intense storms to form along the boundaries where these contrasting air masses meet. Now, a wavy jet stream is not unusual. The jet stream is always wavy to some degree. What is unusual is when the waviness persists for weeks on end without the pattern breaking down and resetting to a more zonal, more west to east flow. What is unusual is when the amplitudes of the waves, the size of the north-south excursions, reach magnitudes that exceed what models predict based on historical behavior. What is unusual is when every forecast keeps showing that the pattern will break down next week, and next week arrives, and the pattern is still there. That is what has been happening in February 2026. The jet stream has been stuck in a highly amplified configuration. Cold air lobes have repeatedly plunged southward over North America. Each time forecasters predict the pattern will relax, it persists instead. And instead of saying, "We do not fully understand why this is happening, and we need to investigate potential external drivers," the communication has been, "This is just a particularly strong example of natural variability. Nothing to see here. Weather is chaotic. Expect the unexpected." Except weather chaos has patterns. Climate variability has statistics. And when those statistics get violated consistently over an extended period, you are not looking at normal variability anymore. You are looking at a regime shift, a threshold crossing, a system operating in a mode that does not match its expected behavior. And that should be cause for alarm, not reassurance. The storm that would later be named Fern began organizing in the third week of January. Meteorologists watched as a low-pressure system formed over the southern plains, drawing moisture from the Gulf of Mexico, while tapping into the reservoir of Arctic air that had been displaced southward by the disrupted polar vortex. The ingredients were perfect: ample moisture, sharp temperature contrast, strong upper-level dynamics, and a jet stream configuration that would allow the system to rapidly intensify as it moved northeastward. By January 22nd, the storm was underway. Heavy snow began falling across a wide swath of the central and eastern United States. The snow was not the light, fluffy kind you can easily brush off a car. This was heavy, wet snow in some areas, driven by strong winds that created whiteout conditions and made travel impossible. Power lines began coming down under the weight of ice and snow. Trees snapped, roads became impassable. And as the storm intensified and moved eastward, it became clear that this was not going to be a routine winter weather event. Over the following days, the storm carved a path of disruption across multiple states. Snowfall totals exceeded 2 feet in some locations. Coastal areas saw flooding as the storm brought storm surge and wind-driven waves ashore. The mid-Atlantic got hammered. The Northeast got hammered. And in the wake of the storm, over 1 million customers were without power, some for days, as utility crews struggled to restore damaged infrastructure in brutal cold. People died. Some died in car accidents on icy roads. Some died from carbon monoxide poisoning after running generators or heaters improperly in homes without power. Some died from exposure, from hypothermia, from the cold that refused to relent even as the storm moved away. These were preventable deaths. The kind that happen when critical infrastructure fails under stress and when weather conditions exceed what communities are prepared to handle. The meteorological mechanics of the storm were textbook. You had cold air at the surface, warmth and moisture aloft, a powerful jet stream overhead, and strong upper-level divergence that allowed the surface, low pressure, to deepen rapidly. The storm tapped into the Gulf moisture stream and converted it into precipitation. Where temperatures were below freezing, it fell as snow. Where temperatures hovered near freezing, it fell as sleet or freezing rain, coating everything in ice. The system was efficient, organized, and destructive. But here is what made this storm more than just another winter weather disaster. The cold air that fed the storm, the Arctic air mass that provided the sub-freezing temperatures necessary to produce heavy snow instead of rain, that cold air was there because the polar vortex had been disrupted and had not recovered. In a normal winter pattern, you might get 1 or 2 significant Arctic outbreaks, followed by periods where the pattern relaxes and milder air returns. But in February 2026, the cold air kept coming in waves because the vortex remained stuck in its disrupted state. The atmosphere was locked in a configuration that favored repeated cold air intrusions, and each intrusion provided the raw material for another potential storm. This is what meteorologists mean when they talk about pattern persistence. Weather patterns are supposed to evolve, to transition from one regime to another, to cycle through different configurations. But sometimes a pattern gets stuck, locked in place by feedback mechanisms that reinforce the existing state rather than allowing it to evolve. And when a pattern gets stuck, particularly a pattern that favors extreme cold and active storm development, the cumulative impacts can far exceed what you would get from a single transient event. The storm also exposed how vulnerable critical infrastructure is to cascading failures. Power grids are designed with redundancy and resilience, but they have limits. When you have heavy snow knocking down transmission lines, ice accumulating on power cables, and sub-freezing temperatures stressing equipment, the system starts to fail in ways that are hard to predict and hard to fix. Utility crews can only work so fast. They can only be in so many places at once. And when the next storm arrives before they have finished repairing damage from the last one, you enter a regime of compounding failures where the system never fully recovers. Think of it like a bridge that gets damaged in an earthquake. The bridge is still standing, still partially functional, but it has cracks, weakened supports, compromised structural integrity. If you give engineers time to assess the damage and make repairs, the bridge can be restored. But if another earthquake hits before the repairs are complete, the cumulative damage can be catastrophic. The bridge that survived one shock cannot survive two. That is what we are facing with the atmosphere in February 2026. One major storm hit, caused damage, stressed infrastructure, and killed people. The system was recovering, and now Giana is forming, poised to hit some of the same regions that are still dealing with the aftermath of the first storm. This is compound disaster unfolding in real time, driven by an atmospheric pattern that refuses to break. The question we need to ask is whether this is just bad luck, a statistical coincidence of timing and geography, or whether we are seeing the early stages of a cascade where each event sets up conditions for the next. Because cascades are hard to stop once they start. Cascades have their own momentum, and cascades in complex systems can lead to outcomes that nobody predicted, because the models were not designed to handle nonlinear feedbacks operating at multiple scales simultaneously. Let me tell you what Giana is and why it matters. Giana is a rapidly intensifying low-pressure system, a bomb cyclone, currently developing off the southeast coast of the United States. The term bomb cyclone comes from the meteorological process called bombogenesis, where a mid-latitude cyclone undergoes explosive intensification, defined as a pressure drop of at least 24 millibars in 24 hours. When this happens, winds increase dramatically, precipitation intensifies, and the storm takes on characteristics more commonly associated with tropical systems: a tight pressure gradient, strong rotational winds, and heavy precipitation in a compact area. Bomb cyclones are not rare. They happen regularly, especially over the western Atlantic during winter months when cold continental air masses collide with the warm waters of the Gulf Stream. The temperature contrast provides the energy for rapid intensification. The jet stream provides the upper-level support. The result is storms that can produce blizzard conditions, coastal flooding, and hurricane-force wind gusts. Meteorologists are very familiar with these systems. Forecasters know how to predict them. Emergency managers know how to prepare for them. But here is the thing about Giana. Giana is forming too far south. Giana is bringing blizzard conditions to the Carolinas, to regions where the climate normals say this should not happen. Yes, the Carolinas get snow, light snow, occasional snow, a few inches every couple of years, enough to disrupt traffic for a day before it melts. But 6 to 12 inches of snow combined with 30 to 40 MEP-sustained winds creating whiteout conditions, that is not in the playbook for this geography. That is a misplaced extreme. Think about the statistical context here. If you look at historical snowfall records for coastal North Carolina or South Carolina, you will find that major snow events defined as 6 inches or more are rare. They happen maybe once or twice a decade, if that. Most winters see no significant snow at all. The climate is simply too mild, too influenced by the moderating effects of the Atlantic Ocean. When cold air does arrive, it usually does not last long enough or penetrate deeply enough to produce major accumulations. The ground is often too warm. The air off the ocean is too warm. The snow falls, starts to accumulate, and then changes to rain as warmer air works its way into the system. Giana is different. Giana is forming in a pattern where the cold air is so persistent, so deeply entrenched, that the usual moderating influences are not working. The disrupted polar vortex has kept Arctic air flooding southward in wave after wave. The southeastern United States has been colder than normal for much of January, and now, as Giana intensifies offshore, it is pulling in moisture from the Atlantic while the cold air remains locked in place. The result is snow, heavy snow in places that rarely see it. This is what I mean when I say Giana is misplaced. It is not that bomb cyclones are rare. It is not that winter storms in the southeast are impossible. It is that the specific combination of a rapidly intensifying, coastal, low-producing major snow accumulations and blizzard conditions in this region is statistically unusual enough to raise questions. And when statistically unusual events start happening in clusters, when the unlikely becomes routine, you need to ask whether the underlying probability distribution has changed. You need to ask whether the climate baseline has shifted in ways that make previously rare events more common. Now, I need to be careful here, because there is a temptation to attribute every extreme weather event to climate change, and that oversimplifies a complex picture. Climate change is real. Global temperatures are rising. That is altering weather patterns in measurable ways, but not every extreme event is directly caused by climate change, and the relationship between a warming planet and specific weather outcomes is often counterintuitive. For example, a warming Arctic can actually lead to more frequent cold air outbreaks in the mid-latitudes by disrupting the polar vortex. Less ice means less temperature contrast, means a weaker vortex, means a wavier jet stream, means more opportunities for Arctic air to spill southward. So even as the planet warms overall, some regions might see an increase in extreme cold events, at least for a period of time, until other factors dominate. The point is that we are in a regime of rapid change where the climate system is being forced away from the stable configurations it maintained for thousands of years. The rules are changing, the statistics are changing, and events that were once truly rare might become more common because the boundary conditions have shifted. Giana might be a harbinger of a new normal, where southeast blizzards are no longer once-in-a-generation events, but something that happens every few years because the atmospheric circulation patterns have fundamentally changed. But even setting aside long-term climate trends, there is something specific about February 2026 that feels like more than just a bad month. The polar vortex disruption, the persistent pattern, the repeated cold air intrusions, the back-to-back major storms, all of it is clustering in a way that feels coordinated. Even though we know atmospheric dynamics are chaotic and uncoordinated, it feels like the planet is stuck in a mode it cannot get out of, like a car that will not shift out of first gear no matter how hard you press the accelerator. The maps tell the story. If you overlay Giana's forecast track with the cold air mass positions, you see a perfect alignment. The storm is forming right where the cold air meets the warm Atlantic. The intensification is happening right where the temperature gradient is sharpest. The snow is falling right where the cold air is deep enough to keep precipitation frozen all the way to the surface. Everything is lining up in a way that maximizes impact, and it is lining up because the larger pattern is stuck. January 26, 2026. Mark that date, because on that day, something unusual happened. Something that does not fit neatly into any single disciplinary framework, but demands attention nonetheless. On January 26th, multiple significant earthquakes occurred around the globe in a roughly 24-hour window. We are talking about magnitude 5.0 and larger events scattered across different tectonic regions, not obviously related by fault systems or plate boundaries, just clustering in time. Now, before we go further, let me be very clear about what this is and what it is not. Earth experiences thousands of earthquakes every day. Most are too small to feel. Many are aftershocks of previous larger events. The planet is tectonically active, and seismicity is part of normal geological processes. On any given day, you might see 1 or 2 magnitude 5 events somewhere on the planet. That is expected. That is background seismicity. What was unusual about January 26th was not that earthquakes happened, but the clustering of multiple larger magnitude events in a short time window across geographically dispersed regions. Seismologists have a term for this: earthquake swarms or clusters. They happen. They are documented, but they are also not fully understood, especially when the clustering cannot be easily explained by obvious mechanisms like stress transfer along connected fault systems or triggered seismicity from a main shock-aftershock sequence. The global seismic network recorded the events. The magnitudes were confirmed. The locations were plotted. And when you looked at the map, it was hard to shake the feeling that something was going on beneath our feet, something synchronous, something that conventional seismology does not have great explanatory power for, because our models of earthquake triggering are mostly local, focused on stress accumulation and release on individual faults, not global patterns operating on timescales of hours or days. Here is where I need to tread carefully, because the leap from correlation to causation is treacherous territory, especially when dealing with complex Earth systems. The fact that multiple earthquakes happened on the same day does not mean they are related. The fact that they happened during a month of extreme atmospheric chaos does not mean the atmosphere and the lithosphere are coupled. The fact that all of this is occurring in the wake of a powerful solar storm does not mean space weather drives seismic activity. But let me ask you this: what if there are coupling mechanisms we do not understand? What if the Earth's systems are more interconnected than our siloed scientific disciplines assume? What if the reason we do not see the connections is because we are not looking for them with the right tools and frameworks? There is a human tendency to find patterns, to see meaning in coincidence, to construct narratives that connect disparate events into a coherent story. This tendency has a name: apophenia, the perception of patterns in random data, and it is a real cognitive bias that can lead us astray, causing us to believe in false correlations and spurious causation. Scientists are trained to be skeptical of pattern recognition without rigorous statistical validation. And that skepticism is essential. It protects us from being misled by noise. But there is a flip side to that skepticism. When you are too skeptical, when you dismiss every anomalous clustering as coincidence without investigating whether there might be a real underlying process, you risk missing genuine signals. You risk ignoring evidence that does not fit your existing models because your models do not have room for that evidence to exist. So let me present the facts without claiming to know what they mean. On January 26th, there was a notable clustering of seismic activity globally. Around the same time, the polar vortex remained disrupted, the jet stream remained highly amplified, and severe winter weather was impacting large portions of the northern hemisphere. This was also roughly 2 weeks after the major solar storm hit Earth and 1 week after the peak geomagnetic activity. All of these events are documented. All of these events occurred in a compressed time window. Now, let me present some speculative hypotheses about potential coupling mechanisms, and I want to stress that these are speculative, not proven, but worth considering. One hypothesis is that geomagnetic storms can influence the Earth's rotation and orientation in subtle ways by altering the distribution of mass in the magnetosphere and ionosphere. Changes in rotation rate or wobble could theoretically alter stress distributions within the Earth's crust, possibly triggering earthquakes on faults that are already near failure. This is a fringe idea, not widely accepted, but it is based on real physics. Earth's rotation is affected by mass redistribution, and seismic triggering is sensitive to small stress changes. Another hypothesis is that atmospheric pressure changes associated with extreme weather patterns can load and unload the Earth's crust, creating stress changes that might influence seismic activity. This is less fringe. There is actually some evidence that atmospheric loading can correlate with seismicity in certain regions, especially where faults are sensitive to small stress perturbations. The magnitude of the effect is debated, but the mechanism is plausible. A third hypothesis is that all of these systems, atmosphere, lithosphere, magnetosphere, are responding to a common external driver that we have not identified. Maybe solar variability influences Earth in ways that go beyond direct heating and geomagnetic storms. Maybe there are cosmic ray fluxes or interplanetary magnetic field configurations that affect multiple Earth systems simultaneously. This is extremely speculative, borderline pseudoscience by current standards. But it is the kind of hypothesis that you might start taking seriously if you keep seeing unexplained correlations. The point is not that any of these hypotheses are proven. The point is that when you see multiple anomalous patterns clustering in time, you should be investigating potential connections rather than dismissing them out of hand. And as far as I can tell, nobody with the resources and expertise to conduct that investigation is doing so, because the question does not fit neatly into any established research program. What we are left with is a series of observations that feel like they might be related but have no clear causal link. A solar storm, a polar vortex collapse, a persistent atmospheric pattern, a major winter storm, a global seismic cluster, and now, as February begins, another major storm forming in a place where major storms rarely occur. Each event can be explained individually as natural variability, but the clustering, the timing, the synchronicity, that is harder to explain away. It is the end of January, and the polar vortex is still disrupted. Forecasts show hints of recovery, weak signals that the vortex might start to reorganize in early February. But we have seen those hints before, and they have not materialized. The pattern has persisted for nearly a month, far longer than statistical expectations based on historical analogs. And as we move into February, the question becomes, what if it does not recover? February is typically the coldest month of winter in the northern hemisphere. The stratospheric polar vortex is usually at its strongest, the jet stream relatively stable. And while cold outbreaks and winter storms still occur, the frequency and intensity tend to moderate as we move towards spring. But that assumes a normal vortex configuration. If the vortex remains weak and disrupted, February could look a lot like January. Repeated cold air intrusions, active storm tracks, temperature extremes, and stress on infrastructure that is already fatigued from a month of above normal demands. Let me walk you through some historical analogs. Winters, where the polar vortex was disrupted for extended periods, and what happened as a result. The winter of 2013-2014 saw a persistent vortex disruption that led to the polar vortex becoming a household term in the United States. Arctic air plunged far south in repeated waves, breaking temperature records and creating dangerous cold across the Midwest and Northeast. The winter of 2018-2019 had a stratospheric warming event in late January that contributed to extreme cold in late February. These events are in the historical record. They have precedent. But here is what makes February 2026 different. The disruption began earlier, persisted longer, and was potentially triggered by external forcing, the solar storm, that is not typically considered in seasonal forecasting. If the vortex does not recover in early February, as models currently suggest it might, we could be looking at a February that extends the January pattern. More storms, more cold, more strain on grids and supply chains. Infrastructure is a particular concern. Power grids have already been stressed by cold weather and storms. Utility companies have had to manage higher than normal demand while repairing damage from outages. If February brings another round of extreme cold and storms, the cumulative impact could exceed system capacity in some regions. You start to see compounding failures. Equipment that was damaged in January fails again in February. Crews that are exhausted from weeks of repairs make mistakes. Backup systems that were designed for short-duration emergencies fail because the emergency never ends. Agriculture is another vulnerability. Late winter and early spring are critical times for preparing fields, managing livestock, and planning planting schedules. Extended cold can delay planting, damage crops that have already been sown, and stress livestock operations that are struggling to keep animals warm and fed. If the cold pattern persists into March and April, which is possible if the vortex never fully recovers, the impacts on food production could be significant. Supply chains are already fragile after years of pandemic-related disruptions and economic volatility. Transportation networks are vulnerable to winter weather, with roads, railways, and airports all subject to delays and closures during storms. If February extends the pattern of repeated winter storms across major transportation corridors, the cumulative delays and disruptions could cascade through supply chains, creating shortages and price increases for goods that are normally taken for granted. There is also a psychological dimension to consider. People can handle a few days of extreme cold or a major snowstorm. They stock up, they wait it out, they recover. But when the extreme conditions persist for weeks on end, when each forecast promises relief that does not come, when it becomes clear that this is not a transient event but a new mode the atmosphere has locked into, the mental and emotional toll adds up. Anxiety increases, resources get depleted, resilience erodes. Now, let me be clear, I am not predicting that February will be catastrophic. The polar vortex might recover, the pattern might break down, warmer weather might return, and this entire month could be remembered as an unusually rough patch of winter, but nothing more. Forecasting is uncertain, especially when dealing with atmospheric states that are already outside normal bounds. But the scenario where the pattern persists is plausible enough that we should be preparing for it. And that preparation starts with acknowledging that we are in uncharted territory. The polar vortex has been disrupted for longer than models predicted. The mechanisms that are supposed to restore equilibrium have not kicked in, and we do not have a good explanation for why, which means we do not have a good basis for predicting when or if recovery will occur. This is where the scientific conservatism that I have been criticizing becomes actively dangerous. If authorities keep saying everything is fine, this is just normal winter variability. Expect things to get better soon. And then things do not get better. The loss of credibility is enormous. People stop trusting the forecasts. They stop following guidance. And when the next real emergency happens, the warnings get ignored because the institution that issued them has cried wolf too many times. A better approach is radical honesty. Admit what we know and what we do not know. Acknowledge that the pattern is unusual and that the persistence is not fully understood. Communicate the range of possible outcomes, including the worst-case scenarios, without sugarcoating or false reassurance. Give people the information they need to make their own risk assessments and preparations. Because here is the thing. If the pattern persists into late winter, if we see another major storm in March, if the cold refuses to relent even as daylight hours increase and solar heating intensifies, we are going to have to confront the possibility that something fundamental has changed. Not just weather variability, not just a bad winter, but a signal that the climate system has crossed a threshold, or that external forcing from space weather or other sources is influencing atmospheric dynamics in ways we have not accounted for. February 2026 might turn out to be the first chapter of a longer story, the opening act of a multi-month or even multi-year pattern shift. Or it might be an isolated extreme that ends in February and gets filed away as an interesting case study. We do not know yet, but we should be watching closely, collecting data, testing hypotheses, and preparing for the possibility that the easy explanations are wrong and that we need to revise our understanding of how the Earth system works. You have watched this far, which means you understand the stakes. You see the pattern. You recognize that something unusual is happening. Now the question is, what do you do about it? First, understand that preparation is not panic. Preparation is rational response to credible information. The polar vortex disruption is real. The persistent pattern is documented. The storms are happening. Taking steps to protect yourself and your family is not overreacting. It is responsible. Second, focus on the basics: water, food, heat, communication. If power fails during the next storm, do you have enough water stored? Do you have food that does not require cooking? Do you have a way to stay warm? Can you charge your phone? These are not doomsday prepper questions. These are practical considerations for anyone living in a region that might experience extended winter weather and power outages. Third, check on vulnerable neighbors, the elderly, people living alone, families with young children. These are the groups most at risk during winter emergencies. A simple knock on the door, a phone call, an offer to help with preparations can make the difference between someone weathering the storm safely and someone facing a life-threatening situation. Fourth, stay informed. Follow reliable weather sources. Understand the difference between a watch and a warning. Know what actions to take when conditions deteriorate. And fifth, maintain perspective. Yes, the pattern is unusual. Yes, the persistence is concerning. But humanity has survived worse winters. Communities have endured longer cold snaps. Infrastructure has recovered from more severe damage. This is serious, but it is not the end of the world. It is a challenge, and challenges can be met with preparation, resilience, and community support. The difference between those who do well during extended winter emergencies and those who struggle often comes down to mindset. People who stay calm, who adapt to changing conditions, who help their neighbors, who maintain hope even when things are difficult, those are the people who come through strongest. So prepare, but do not panic. Stay informed, but do not obsess. Help others, but take care of yourself first. And remember, weather patterns, no matter how persistent, eventually change. Spring will come. The vortex will eventually restabilize. The cold will break. The question is just how long it takes and how much disruption occurs in the meantime. As we close, I want to leave you with the questions that keep me up at night. The questions that mainstream science is not asking loudly enough. Why has the polar vortex not recovered? What mechanism is sustaining the disruption beyond the normal timescale? Is there a connection to the January solar storms, or is that just coincidence? Are we seeing the early stages of a more fundamental shift in atmospheric circulation patterns driven by climate change, weakening magnetic fields, or some combination of factors we have not identified? What does it mean when multiple Earth systems, atmosphere, lithosphere, magnetosphere, all exhibit anomalous behavior in the same time window? Are these systems more coupled than we think? And most importantly, are we prepared for a future where extreme weather events cluster more frequently, where the gaps between disasters shrink, where the assumption that things will return to normal no longer holds? These are not easy questions. They do not have simple answers, but they are the questions we need to be asking if we want to understand what is happening to our planet in February 2026. The polar vortex will eventually recover. Winter Storm Giana will pass. Life will go on. But the pattern we have witnessed this month, the persistence of the disruption, the clustering of extreme events, should serve as a wake-up call. The Earth system is complex. It is interconnected, and it is capable of surprising us in ways our models do not predict. The question is whether we will learn from this experience, whether we will invest in the research needed to understand these connections, whether we will build the resilience needed to face an increasingly unstable climate, or whether we will simply wait for the next disruption, the next storm, the next month when everything goes wrong at once and we are left scrambling to understand why. The choice is ours. The data is there. The questions are clear. Now we just need the courage to pursue the answers, wherever they lead. Stay safe, stay prepared, and stay curious, because the planet is speaking, and it is time we started listening. And that's what separates those who survive comfortably from those who barely survive at all. The cold is coming, the pattern is set, the physics is in motion, but you're ready now, and that makes all the difference. Stay warm in the days ahead, stay prepared, stay connected with people who'll check on you and people you'll check on. Community survives better than individuals. Prepared families survive better than unprepared ones. Calm awareness serves better than panic or denial. You have all three now. Use them well, and come back here as weather develops, because we'll track this pattern together and share information that helps everyone navigate whatever the coming weeks bring. This winter could become one that meteorologists study for years. Let's write ourselves into it as people who saw it coming and prepared and helped others do the same. That's who we are. That's how we face challenge together, prepared, unafraid, ready.